Okay, so we are going to do an example that's going to walk through the process of designing a chain drive now. Now here we're going to use this charts in the book. We're not going to be using a vendor's catalog, and we are going to use the Excel spreadsheet that we see here. You can download it from Canvas. The problem statement is going to start at the bottom of page 286, and then we've got a little bit of illustrations then on the following page as well. So I'm going to go underneath here. We're going to look at our application. And it's going to say that figure 737 shows a drive of a heavy loaded conveyor for use in the fields of a large commercial produce farm to take heavy containers of potatoes from the field onto trucks that will transport them to a processing plant. The conveyor is to be driven by a gasoline engine delivering 15 horsepower at a speed of 900 RPMs. The conveyor pulley speed is to be between 230 and 240 RPMs. Design the chain drive. So we're going to go over here to the illustration, and this is what we're dealing with. So we need to determine what are the sprocket sizes, what is the chain length, and what is the chain size. Okay. So, using that information, what we're going to do is we're going to open up our spreadsheet because it follows the process for this particular example. So at the very top here are input data. We're going to be putting in what our driver and our driven machine are. So our driver in the problem statement, what did it tell me? What kind? Just a name of a driver. It's a gasoline engine. So we're going to want to put this in here. Okay. What about our driven machine? Heavy loaded conveyor. Did it give us an input speed? 900 RPMs, good. And input power, 15 horsepower, good. Nominal output speed of our driven machine. So it's between the 230, 240, right? So what should we put? 235, yeah. Sounds good. And then service factor. Now you'll notice that it says we're going to be, we need to go to table 717 on page 286. So right above that problem statement, we are going to find our service factor. So again, this is looking at kind of that input and that output and the chances of, bad things happening. So as we look here, we're going to find our driver type. Our driver type is a gasoline engine, so it's going to be in the last column. And then we have heavily loaded conveyor. Probably moderate shock. We see heavy conveyors here, right? Yeah. So we're going to go all the way over to the right. So 1.4 seems to be a good number based on the description we have. As the designer on something out in industry, you might have more insights and, better information that you could go on and be more accurate, but we're going to go with 1.4. Now, what that does for us is it multiplies the 1.4 times the input horsepower that we had. And now this is our design horsepower that we're going to use in the charts. Okay. Now, additionally, this is the speed ratio based on our nominal output speed, So now what we want to do is we want to take this 21 design horsepower and we want to find what our chain pitch is going to be. Now, this is in inches. So remember, chain is called out in number, and then it corresponds to a pitch in inches. So they're going to be looking for the inches here. So we're going to go back to those three charts starting on page 283. And we're going to use this 21 horsepower. Go underneath. So the first one that we have is a number 40 chain, which is about, this is the size that I had here. Okay, that's about the size of that, or that is the size of a number 40 chain. And we're going to see if we can find, and we're going to look specifically down the column of 900 RPMs. We're going to see if we can find anything that's 21. Not, right? The chart ends at 17. So this is not large enough chain for our application. So we're going to turn the page because the next chart is a bigger chain. It's number 60 and it's 0.75 pitch. So it's gotten a little bit bigger by 1/4 of an inch. And we're going to go down it's in between here, between 800 and 1000. And we're just going to look and we're going to see, do we see 21s right about here, right? We start to see 21s on one side or the other, right? So yes, this chart, and we're kind of, I like the position, we're kind of in the middle-ish of this chart, which is nice. So it seems like that would be a possibility. But let's look at the last one and see where we're at there. So if we look here at the top, you're going to see we have our 900 here, and this chart starts at 23 horsepower, which is larger than what we actually need. Now, I don't know that that would be a bad idea, that it wouldn't be applicable, but notice where we are on the chart. We're at the very top and probably in that window of maybe over designing if we go to that big. Okay. So probably the best is going to be our 60. Okay. So 60, number 60, but it's 0.75 pitch chain. So going back to our spreadsheet, we're going to put 0.75 in that cell. Now, number of teeth on the driver sprocket. Okay, let's go back to our chart. You'll notice here that we don't have a 900 column, right? So we've got an 800 column, we've got a 1,000 column. And where we would find the 21, okay, would be like right about here, right? Right about here. It's going to be between those values. And you'll notice if I go over to the left, my number of teeth on that sprocket are going to be 18. Okay, 18. So we're going to say number of teeth is going to be 18. Rated horsepower. Okay, now we've got to know what is the horsepower of this when it's going 900 RPM. So what we're going to have to do is we're going to have to do just a really quick ratio. I'm going to go back underneath. It's not hard to do. But if we know that 800 RPM is going to have 20.7 and that 1,000 is going to have 25.73, we want to find out what is the horsepower at 900. So I'm just going to use the variable X and I'm going to put it over 900 RPMs. It's going to be equal to, and now I can use really either one of these. I'm going to use the 1,000 just because, and I'm going to put my 25.73 horsepower on top, divided by 1,000 RPMs. Okay. Now to solve for X here, I'm going to multiply both sides by the 900 RPM. So this is going to multiply up. And now these RPMs are going to cancel out. So I'm going to multiply 25.73 times 900 divided by 1,000. And what do I get for my value of the horsepower for 900 RPM? What is it? 23.16 horsepower, right? Okay. So that's going to be my number then that I'm going to put in there with that 18 tooth. Does that make sense to everybody? Okay. If we were reading and the 900 was directly on there, it happens to be the one chart. All the other two have 900 columns, but we have to do this. So back underneath here. So this is going to be 23.16. Okay. Now, the other thing it's asking for is what is the lubrication type? So the lubrication type, we're going to read off of that chart by just being in that range. So you'll notice that we landed right here. So if we go down to the bottom, that's a type B, which is a bath or disc lubrication. So you can just put in type B. Okay. All right. Any questions so far? Now we're going to go down and it's going to say, okay, based on that, if you would, that speed ratio or the output speed, target the nominal output speed of 235, you will need 68.936 teeth on your driven sprocket to create this ratio that you have here. Well, obviously we can't do 68.93. So we need to go to the next integer number. So we'll just do 68. Okay. And we'll look. If I put 68 in, I want to go down to my actual output speed. And I want to check, is this in between the numbers that they wanted me to be in? So is it between 230 or is it between, was it 230 and 240? Is that what it was originally? Yeah. Between 230 and 240. So we are within that. Okay.
For that or?
Not for this one. No. So then we have the pitch diameter of the driven sprocket. It automatically calculated it for us based on the size. And then now we have our pitch diameter of, our driver and then our driven. So the driver is going to be the smaller one. The driven is going to be the larger one. The next thing we need to do is determine a nominal center distance. Now here again, in our problem statement, they did not give us a center distance. So if you recall, and I have the note over here, you want to pick a number based on 30 to 50 pitches. Now, we have to look back. We picked a 0.75 inch pitch. So we have to multiply 0.75 by 30 and 40, and that's going to be the range that we have to be within. So if we do that, we want to be, oopsie, what would we be? 30 times 0.75. What do you guys got? 22.5. So that's going to be the smallest center line I want. And then if I take 0.75 times 50, right? What's that number? Okay, so between those two numbers, between 22.5 and 37.5, what center distance do we want? You guys are the designer. 30. Okay. And that's going to be, we have to put pitches in here. Oh, right. Oh, I was thinking center distance already because center distance is coming. Dang it. I'm sorry. So we just need to put pitches. So between 30 and 50, what do we want? 35. I heard 35. Okay, we'll do 35. Sorry about that. So now we have our computed chain length in pitches. So this is the number of pitches I would count. And the number of pitches they have here is 114.8. So as we know, we can't have 0.8 of a pitch. So we're going to put this to the nearest integer number. And it says here, it's suggested that you use an even number. So we'll just do 114. So now the theoretical center distance. So center to center is going to be 34.3 or 0.587 or, oh my gosh, 34.584. And then the theoretical actual center distance, and that's going to be the pitches. And then the theoretical center distance that is going to be, or the actual, you guys see what I mean? So 25, almost 26 inches on our center distance. And then the number of pitches is going to be that 34. So it lands within that range. Okay. So now at the bottom, design review, so that we can specify everything that we did here. Number one, we're going to have to put our chain pitch. So you're going to have to populate this with the equal and then find the change pitch on the top. The chain length in pitches, and then the driver sprocket pitch diameter in inches, the number of teeth, the pitch diameter of the driven, number of teeth on that one, and then the center distance, the distance between centers of the sprocket in inches, and then lastly, the type of lubrication and the number of strands. In this case, we'll only have one because we were able to accomplish it with the horsepower. So that, are there any questions on this one? I'll kind of scooch back up here in case you need to see any of the numbers. Okay.
So are we pretty much always going to be doing one strand?
You don't have to. It depends on your application. So if you end up with, let's say, a really high horsepower or a higher horsepower than you can accomplish with any one of those, in our case, the 3 charts, then you're going to have to consider multiple strands using the factors that we had shown. Yeah. I don't think you need to do it for the example or for the assigned problem that I have for you, but we'll look at that in a little bit. Okay, so this is your last practice problem. And so you're going to want to take your screenshots and then make sure that you fill these with not just the numbers or the values. You want to actually program that in so that it pulls it from the top so that when you use this for your assignment, it's automating it for you as well. Okay, so I'm going to stop there with this example, and then we'll be back and we'll look at the homework that you have assigned.